There we go. So YouTube should be streaming in about 10 more seconds. So if people are watching YouTube, it should be working. Good morning. Good morning. All right. So today's lecture. Okay. So at this point, I just want to kind of zoom out a little bit and look at the pine forest instead of individual trees. So at this point, we have just talked about C control structures. So when I talk about C control structures, I basically was talking about conditional statements, the if statements, while statements, and do while statements. And somebody would probably say, but there are more statement types than just that. Okay, there are switch statements, there are for statements, and so on. Well, the answer is yes, okay, but the for statement for the most part is a fancy while statement, so I'm not even going to bother to talk about the for statements. And then the switch statement is kind of unique in a way because there are I personally do not like to use switch statements in C unless it is really the correct control structure to use, and those are fairly rare. Okay, so we'll just kind of focus on conditional statements because for the most part, not entirely, but for the most part, conditional statements can do what a switch statement does. The one thing that a conditional statement does not do that a switch statement can easily do is to have one case falling through to another case intentionally. But that's the thing about switch statements in C is if you don't have a break at the end of one case, it just falls through to the next case, which I think is not really a very good design because that's just asking for trouble in my opinion. So anyway, so we only have if, while, and do while. Okay, those are the only three control structures in C that I would like to talk about. So we might think, well, then we're all done, right? I mean, that's all the, and then we talked about all the conditional statements. We talked about, how to change a complex conditional statement that has negation, conjunction, or disjunction into simpler ones. Eventually boil everything down to comparisons. Okay, so we talked about that also. So it would seem that we are pretty much done with C, right? Well, not quite, okay? Because one really important concept in C and C++, I mean, you're looking at the live cast or the recording, and the one thing that we haven't talked about is how to call and return from subroutines. Okay, so now it would be a kind of interesting point to just kind of digress a little bit and talk about why this is important, okay? Well, generally speaking, why is this class important? And to be more specific, why do we want to know how to call and return from subroutines in a way that is compatible with the C programming language? Okay, so that is what we'll be talking about next. It's digressing a little bit to something that does not seem to connect to this class, but I think it does. Okay, so I'm just going to the Power Server, going to my account, and just that. Okay. Oh, okay. I guess that didn't work. I have to remember the link then. There we go. So if you go to this particular URL, you can actually see all the details as well. So there's one thing that I want to mention in specific over here. Most of these are remnants of things that I did when I was teaching at UC Davis. I was teaching the micro mouse design class over there for more than 10 years. I think I started sometime in 95 or 96, and I stopped teaching over there in about 2008 or 2009, right when the UC system had a financial crisis, and the first thing they did was to basically let go of all the lecturers, all the part-time and low salary people. They let those go first. Well, that was a very wise move. No, that's not exactly what I meant. That was meant to be cynical. Anyway, so we go take a look at the real-time kernel. And if you're not familiar with what is a real-time kernel, it is a miniature operating system. For the most part, if you're talking about a real-time kernel and you're comparing it to an actual OS, an actual operating system, the difference is a real-time kernel only has the provision to deal with threading, multi-threading, and not really it's not a full implementation of an entire operating system. The one major component that is missing from what we call a real-time kernel is a file system. So most real-time kernels do not come with a file system. You cannot create files, you cannot delete files, you cannot read or write files. So there are no such thing as files in a real-time kernel. What a real-time kernel does, and what it does really well, is to manage threads. Okay, we don't have any classes that teaches multi-threading programming. Not here. If you're transitioning to SEC state in the future, you will probably take a class called systems programming, and that one touches on multi-threading programming just a little bit. But what a real-time kernel does is to allow you to have multi-threads in a program, and one thread you can just kind of look at it as a subroutine running, and it is running in parallel to other subroutines in the same program. So that's basically multi-threading in a nutshell, is you can have subroutines running quote-unquote in parallel with each other, and they can all call other subroutines, they can all access the same global variables, and so that's basically the bottom line of multi-threading, as opposed to multi-processing. Okay, multi-process and multi-thread is different. There are various concepts involved in a real-time kernel, and this is not a good time to talk about this. But what I do want to talk about is the API of this particular real-time kernel. In other words, if you're writing a program entirely in C or C, well, actually just C in this case, but I think C++ will work as well, is how do you interact with the real-time kernel? In other words, I just want to create a new thread right now. I want that subroutine to run in parallel to main, okay? And how do I do that? Well, the way to do it is to call this particular subroutine. So this is the API, for adding a thread to the real-time kernel, and you can see, all of this is fairly C type of concept. There's nothing here that is specific to assembly language programming. We have a structure. T is a pointer to a struct thread. Q is a pointer to a struct queue. SP is a void pointer, and then we have a start is a pointer to a subroutine that returns void, but it also takes a void pointer as a parameter. We talked about pointer to functions just a little bit in the previous class, and then we also have a void pointer that points to we have a parameter which is a void pointer as well. So here's the description, and I'm not going to get into the description, okay? But when you look at the API, it is, well, that's fairly C-like, okay? Or if you look at something else, let's take a look at semaphore operations. So we can look at a semaphore, a P operation, okay, RTK semaphore P, which performs what we call a P operation on a semaphore. These are concepts, for synchronizing operations when you have multi-threading. So you can basically lock threads out of each other's way. Because there are things called critical sections where only one thread can get in at any particular time. So we have control mechanisms so that we don't end up with threads basically stepping over each other. So this is a synchronization mechanism. And it's kind of interesting in many ways because a P operation can quote-unquote block, which means whoever thread is calling this subroutine can be put on quote-unquote put on the shelf, okay? Because somebody else is already in the critical section. So if a subroutine or if a thread wants to access the critical section when somebody else is already in the critical section, the second thread that's trying to get into the critical section now has to wait until the other thread or threads are done. Then it can go into the critical section and do whatever it needs to do. Okay, so enough talk about that. So now the question is, how is this all implemented? And you probably get the answer. The entire real-time kernel was written in assembly, and the way it works is that the assembly code of the real-time kernel is compatible with how C calls subroutine. And that is why it is an important topic, because for every single operating system, okay, I don't really care which one you're talking about. You can be talking about Windows, you talk about Mac OS 10, you can be talking about Linux. The lowest level portion of an operating system is always written in assembly. Okay, the only question is how much. Okay, in Linux, that portion is relatively small. Okay, so that means you're porting Linux from one architecture to another architecture is relatively a simple task. Okay, doesn't mean it's really simple. It's just relatively simple compared to some of the other operating systems. iOS and also Mac OS 10, they're both based on Unix, which structurally share a little bit of similarity to Linux, so they're also fairly easy to port. Windows, on the other hand, because it's a proprietary operating system, nobody knows exactly what the source code looks like except for Microsoft and its employees. So, but I have a strong suspicion that it is not. There's a significant portion of code that is written in assembly, and that makes porting Windows from one architecture to another architecture a really kind of expensive operation from Microsoft's perspective. Okay, but this is the kind of job that you can take on when you know how to write code in assembly, but not only that, you know how to interface C code and assembly code seamlessly. Now, when I say that, to be more specific, I'm talking about having C code to call subroutines written in assembly, and vice versa, having subroutines written in assembly to call subroutines that are written in C. So you have interoperability between C and assembly code. That is a very interesting skill set. Do we need every single programmer out there to know this? The answer is no. Okay, but people who do know this type of programming and kind of enjoy this type of programming, they have more options when they want to look for jobs. Okay, and personally, I think those jobs are very, very interesting. I like to work with low-level code compared to high-level code, and so this type of coding, really kind of interests me. So that's just what I want to share with you guys. Is the rationale of why do we talk about this? Okay. And this entire real-time kernel was written in about a summer, so I cannot say that it's really fast. But it was it's my hobby to write this kind of code. Okay, so enough mentioning about enough digression. So now we want to look at this particular C program right here. And I don't think anyone has any question of what it does, right? We have main, and main is going to call f is going to return to main is going to call f again, and f is going to return to main again, and then we are done. Okay, so well, what is the point then? What is the point of this particular sample program? The point of this sample program is to illustrate what a subroutine needs to do and what a caller needs to do in order to support subroutine calling and returning. So we have already talked about, I would say, most of the instructions that we need to get this implemented, but not all. Okay, there's only one single instruction that we haven't really mentioned. Well, we have mentioned it, but we haven't really explained and played with it. So that's the only one instruction that is missing, but we have everything else to do this. But before we get back to the coding of the subroutine, we'll take a quick digression. So the digression is to talk about the concept of a stack. Okay, a stack is basically known as a last in first out kind of a storage. So last in first out is pretty easy to understand. If you have ever been to a buffet, okay, and you look at a stack of dishes, that's last in first out. Okay, the very first dish that the restaurant put onto that stack at the first, when they first open, it's going to be the last one retrieved by customers. Okay, and then the hot, freshly washed plate that they just put on top of the entire stack is the first one to be taken by the next customer who needs a new plate. Okay, that is last in, first out. I'll give you two more examples and then we'll move on. The two additional examples are things that we should all understand because we have all done something like that, in our lives. The first one is the refrigerator. So, let's just say that you went to the supermarket or you went to Costco and you bought a whole bunch of stuff, okay, that needs to be refrigerated. And unless you're a very disciplined person, and you look at everything that's already in the refrigerator and you say, well, this is, this has an early expiration date and we should put it to the front of the refrigerator, take everything out, put all the new stuff that you just bought, put it in the back, and then put everything back in, okay, in the right order. Most people do not do that, right? Well, I certainly don't, even though I should be. So if you don't do that and you just say, okay, I'm just going to put everything that I just bought into the refrigerator and without moving things around, that means your refrigerator has just become a last in, first out storage or container, okay? So that means, that little pack of cheese that is kind of in the back of the refrigerator will probably never be seen again, okay, until you're ready to move, because then you have to empty out the entire refrigerator, at which point your cheese is going to become a mold garden. You're going to have mold of every colors in that cheese, in that pack of cheese, okay, because you have just turned your refrigerator into a last in, first out container. So things that you bought 5 years ago that are sitting in the back of the fridge would not be retrieved, okay, anytime soon. But guess what? That new jar of pickles that you just bought, well, that's going to be consumed and be out of the fridge in no time, because that's the first thing you see and retrieve when you're thinking about, oh, I just need a quick snack. So does that make sense to everybody? Does everybody understand what a stack or last in, first out container, how it behaves? Okay, I'm not seeing any questions. I get one yes, okay. But I did promise another example. So the other example is a U-Haul truck. So we have all moved or helped somebody else moved, right? So if you put so let's just say that you put something into the granny's nook, okay, which is the one little thing that the bump, that appears to be on top of the cabin, okay. So you put something over there and then you pack the rest of the truck, right? And then when you're ready to hop into the driver's seat to drive to the destination, then you just remembered the one thing that you put into Granny's nook, on a U-Haul truck, was the map to the destination. Now this is assuming that we don't have GPS technology and the rest, okay? So you need that map. Well, good luck, empty out the entire truck to get to that map that you put into the truck first thing, okay? Because a U-Haul truck is inherently a last in, first out container as well. That bike that you just push in before you slam the tailgate or the tailgate of the truck is going to be the first thing that falls out of the truck when you open it, okay? So it is last in, first out. The last thing that you put into that container is the first thing that you retrieve from that container. For those of you who have taken CISP310, which mentions the concept of a stack, this is not that kind of a stack, okay? We are talking about a much low-level kind of stack, which is implemented by these three definitions. So we have these three definitions over here in C. One is merely just a macro to tell us what is the size of the stack, what is the capacity of the stack. So in this case, the capacity is 32 items. What kind of item are we storing in the stack? Okay, in this case, we are storing bytes on the stack. So one item on the stack is a byte. And then we have something that is called a stack pointer, okay, which is probably something new to all of us, to all of you. So what a stack pointer does is to keep track of, well, which part of the stack is quote unquote in use. And by the way, where is the last item that I push on the stack that is still in use? So that's what the stack pointer is really doing. Is it's more or less like a bookmark. Okay, if you consider, let's say you have a binder. Okay, not a binder, but a notebook. Okay, so let's say you have a notebook, and you want to use the notebook as a last in, first out container. So you start to write on the first page, okay, which is the first page that is in use on the stack, and then go like, I need to remember something else. You turn the page, you go to the second page, you write something on the second page, and you go like, I need to remember something else. You turn to the third page and you start to write something. So at some point, you go like, how do I keep track of where was the last page that I used, because I need to close the notebook to put it into my backpack to go to school. So when I get to school, I still want to remember where the last page was, on the notebook that I was using. So you introduce the concept of a bookmark, and that's what the stack pointer is. It's basically a bookmark that marks the page that you have used last. Okay, so as you turn to write on additional pages, you move the bookmark along so that when you get to school, you retrieve your notebook from your backpack, and you just have to go to the bookmark and go like, oh, okay, this was the last page that I wrote on. Then you can continue to either retrieve content from the notebook, or you can continue to write additional pages on the notebook. And every time you use a new page, remember to move the bookmark. That's what the stack pointer does. Okay. So now we can look into very specific code to push and pop. Okay, pushing basically means we are storing something in a stack. So for the most part, you can look at a stack as a last in, first out, quote unquote, container. So as a container, a stack is not useful basically on its own. It is only here to help you store things and to retrieve things. Okay, so it's a container. In this specific case, the way we store something, now how do we know we are storing something? It's because of the second statement right here. So the second statement says wherever the stack pointer points to, we're going to store some value x. Now what x is not really important. The important part is x gives us a value that is a byte, and we are storing that byte to whatever the stack pointer is pointing to. But Tech, didn't you just mention that the stack pointer points to the very last thing that we just stored on the stack? Isn't this operation, the highlighted operation, going to overwrite something that we have just stored on the stack? The answer is yes, but we have another operation that precedes this one, right? So we have a SP minus minus. In other words, we are subtracting, we're decrementing the stack pointer, then we store something into the new location that the stack pointer is pointing to. So if the stack pointer was already pointing to the last thing that we stored on the stack, hey, this is not a problem because I just moved the stack pointer before I store something new on the stack. But this is where things get a little bit confusing, because most people think that if the stack is empty, the stack pointer should be initialized to the beginning of the entire array. Okay, the array that I'm referring to is stack over here. And as we put more items on the stack pointer would increment. Okay, and then when the stack pointer points to the last byte of the entire stack, then the stack is full. Okay, we cannot store another item onto the stack. So this is what we usually intuitively think that we should use something. Okay, we start on page 1 and then we go to page 2 and so on. But the way we use a stack in assembly language programming and in all computer architecture that I know of, okay, so this is not specific to the toy processor. This applies to the ARM processor on your cell phone. It applies to the A13 processor on your iPhone. It applies to any processor, okay, the Intel processor on your PC. Okay, they all use a stack from the high address down to the low address. Okay, so before we get back to that point, then let's go take a look at how you retrieve an item from the stack. Okay, Jared has a comment here. Yes, there's a semicolon after that I did not put into the the code here. So to be more specific, there should be a semicolon here to make the syntax correct. Yes, so good catch, Jared. I am very tempted to fix the problem right now, but that's going to affect the flow of the lecture, so I will have to kind of remember to do that. All right, so how do we retrieve an item from the stack? Well, the first thing we do is, because remember what I said, the stack pointer points to the very last thing that I put onto the stack. So it kind of makes sense that if I want to retrieve something from the stack, this is the first operation. Okay, just dereference the stack pointer and then store the value of whatever the stack pointer is pointing to into X, okay, or use it by the way for something else. I don't really care what you do with it, but this is how we retrieve the last thing that we pushed on the stack. But this is the other operation, okay? You have to follow up with SP++, because when we retrieve something from the stack, that means it is quote-unquote used, and something that is already used is not going to sit on the stack any further. And to deallocate that location and basically say this page is not in use anymore, we increment the stack pointer. We move the bookmark and basically say, oh, by the way, anything that is below where the stack pointer is pointing to is really not in use. Now, is it a part of the stack? Technically, it is not. It is not actually part of the stack that is in use, but it is part of the memory space that was allocated to the stack. Okay, so does everybody understand what I just said? There's a difference between what is quote-unquote in the stack. When we say that something is in the stack, it means it is in use in the stack. Okay, so I think this is when Zernal comes in handy. So here's Zernal, and what we'll do is we are going to have a pictorial representation of the stack that we just talked about. Okay, so let me try to maximize the area, so this way it's easier for me to draw things. Okay, there we go. All right, so we're going to draw a stack here. Okay. To be more specific, this is the stack that we just mentioned. So, so the word stack, okay, the identifier stack, which is the name of the array, really refers to the very beginning of the entire array. So if I want to put the indexes over here, this is square bracket 0, square bracket 1, square bracket 2, and the very last one is square bracket 31, because we counted from 0. So you can kind of fill in the rest if you want to. Okay, so this is one location, this is another location, this is another location, this is the very, very last location that belongs to the stack. So are we good with this picture? Does everybody understand what this picture is representing? Okay, cool. All right, so what we are going to do is to say, well, let's just look at push and pop operations. Okay, so let's just say that at some point in the execution of this particular program, stack pointer, which is a pointer that can move around, is pointing to this location. I don't even know nor care the index of this item, from the array's perspective, because the stack pointer is really just a pointer. It is not an index into the array. It is really just a pointer. So now the question is, what are we going to do when we push something on the stack? I'm just going to repeat what my notes already mentioned. So to push an item, which is basically to store an item onto the stack, we perform two operations. The first one is to quote-unquote allocate the space for the new item that I want to store. So that involves a minus SP or SP minus minus. Doesn't matter which way you want to call it, okay? Because it has the same effect. I'm not using the value of the expression, so we are only relying on the side effect of minus SP. So whether it's a pre-decrement or post-decrement, that really does not make a difference in this case. So I'm going to use green color, okay, to represent what we are doing. So what we're doing is we're changing SP to point to a lower location, okay, with the first step, And then the second step is to say whatever the stack pointer is pointing to is going to store, I'll give it a very specific value in this case. Let's say we're storing 42 in decimal over here. Okay, so what that's going to do in our picture is we are now saying that, oh, whatever the stack pointer is pointing to at this point after the after the decrement, is we're going to store 42, in decimal into this location. That's a push operation. So the green part is corresponding to a push operation. So are we good so far? So if we want to push another item on the stack, okay, so we now have another minus SP. Oops, wrong color. Let me go back to the correct color. So if I want to push another item, I just have to repeat this particular sequence of operations. So in addition to 42, we have a 7. Okay. So now, in terms of the picture, we move the stack pointer again to point to the byte right below the one that it was pointing to, and now we store a 7 over here. So this means the stack, quote unquote, grows downward. Okay, we start at a high memory location, and as we store items onto the stack pointer goes lower and lower. Okay, and at some point when the entire stack is used, the stack pointer would be equating to stack the array itself, and at that point the stack is full. Okay, it's being used at capacity at that point. Okay, so what about the pop operations? So the pop operation is referring to retrieve. Okay, so there's store and there's also retrieve. So when we say pop, it means that we are retrieving an item from the stack. So it's doing exactly the opposite. Okay, so if I want to do a printf statement, okay, for those of you who, okay, most of you know cout better than this. Okay, so we can use a cout. Okay, so when we say cout and then star sp, and then we basically say, okay, this particular byte on stack is already used and we don't need it anymore. So we have a plus sp following that. Okay, so when we perform this operation, what we are doing, I'm going to use the color red to represent this. So we are retrieving this 7. Okay, so 7 is printed. Okay, so we want to send this to cout or standard out. And then the next thing we do is we are changing the stack pointer back to a higher location. Is that okay? Does everybody understand what this is doing to the stack? It's color coded. Okay, these are in green. Oops, let me use the wrong place. So these are in green, and to pop is in red. Okay, everything is good so far. All right. So if I want to perform the same operation again, cout less than star sp, and then plus sp again. And once again, this is a pop operation and it's in red. So the first thing we do is we retrieve the value and utilize the value. So we're going to print this out. So on your console, you will first see a 7, then you will see a 42. But remember, we also have to adjust the stack pointer so that it is now incremented. Is that okay? So if I perform these operations in exactly this order, okay, then I will print 7 first, then I will print 42 on the console. Okay, so assuming that this is all okay, the next question, which is very important, is, well, how do we initialize the stack pointer? Okay, what does the stack look like when it is empty, when we haven't stored a single item on the stack? So this is kind of tricky, right? Because the stack pointer, by definition, points to the last item that we have stored on the stack. But we haven't stored a single thing on the stack. So where should we put the stack pointer, or where should the stack pointer point to when we really have not stored a single item on the stack. So to answer the question, you have to think about, well, the stack may be empty right now, but the next push operation should use the first location available to store something on the stack, which is going to be this location over here. So I'm going to use blue to kind of indicate that this is the location where we want to store the very first item that we push on the stack. But because a push operation is always starting with --SP, then we store to whatever the stack point is pointing to. So that means when we want to initialize the stack and say that, oh, this stack is empty, we haven't stored a single item onto the stack, this is where we want the stack pointer to point to, which is the 1 byte that is past the end of the array. Does that make sense? Because if we do it this way for the initialization, so I'm going to use blue to color code the initialization. So the initialization of the stack pointer is simply SP equals to stack plus the capacity of the stack, which is stack size. This is one way to do it. But if you prefer the array method of looking at the stack, you can always say it is the address of stack bracket stack size. Not stack size plus 1, just stack size, because stack size is already the index of the element that should not exist in the array, because we start counting from 0. Is that okay? Are we good so far? All right, so I'm not seeing any questions, which I'm going to assume that everything is good. Okay, thank you, Richard. All right, so we have just talked about the concept of a stack. How is it useful, right? I mean, how is the stack useful in this case? So the next thing we want to do is to take a look at the execution of a program in C, to be more specific, the sample program that we have just mentioned. So we're gonna take a look at the very simple sample program, which is the same one that I have just mentioned, and we'll just go ahead and write the program like that. We have void f, it's an empty function. Then we have int main, which is going to call f twice, once, twice, and then return 0 from main itself. This is the entire program. We'll use GCC to compile the program, warn all -g, so that the debugger has the symbol table to do the debugging, -o stack, and then stack.c. Program is now compiled. Use GDB to take a look at the execution of the program. And we are now looking at the listing of a program. We'll put a breakpoint on line 7. Now you can also put a breakpoint on main itself, which basically means when you run the program, it will stop, or I should say it will pause right away, so that we have control over how we want to proceed at that point. So that works. We run the program, and quite obviously it's going to stop on line 7, because that's the first line that we can pause on. Okay. So not very surprisingly, okay, single step, we go into the subroutine f itself, single step again, we get back onto main, single step again, it goes back into the subroutine, and then single step, it goes back into main, but this time it goes to line 9 and not line 8. And then if we single step again, the program is going to conclude, and we're done. Okay. So we see this particular message here because it's trying to trace beyond the end of the execution of our own program. So it's trying to trace to where main is returning to, which does not have the source code available, and that's why it complains about it, because I did not install the source of libc, and as a result there's no source code to track into. So but that's perfectly okay. If I just do a C, which is continue to execute until the program is all done, it's just going to say it exited normally and everything is good. The execution of this program just concluded. So what does this have anything to do with stack, right? So let's find out. Okay, so we're going to go back into the C code, but this time we're going to annotate it and start to use the concept of a stack. Okay, so this particular operation, you're just calling f the first time. Let's see what is involved in the actual process of doing this. The first thing we need to do is to say, remember where the subroutine, where f should return to. So we are storing this information somewhere, okay, and then we continue execution in f, okay, which you already know that a jmpi instruction can just do this, right? Your jmpif is going to continue execution at the label f. So now the question is, what do we do in f? First, absolutely nothing, because the subroutine is empty. It doesn't do a single thing. But when it is time for the subroutine to go back to the caller, it has to somehow retrieve where the subroutine needs to return to, assuming the caller already stored this somewhere. Okay. And then the next thing it needs to do is to continue execution based on this return address. Okay, so return address is basically referring to what we just retrieved, where the subroutine is supposed to return to. Okay, and what do we need to do with the second call? Same thing, right? So like that. So now the question is, where am I going to store this information? Okay, because when we use the word remember, it's kind of the same thing as storing, right? And in the context of a stack operation, storing is pushing. So that is where we say, oh, so remember basically means the same thing as push. So when we mention the word retrieve, it's really the same thing as the word pop, okay, in the context of stack operation. Is that okay? So the caller, main in this case, is responsible to push where the subroutine is supposed to return to, and then the subroutine makes the assumption that that information was already pushed on the stack, and it will simply pop the return address from the stack and then continue execution to where the address is. So are we kind of doing okay with this? Maybe. I think this is not the kind of concept that that's introduced in CISP300 or 360 unless I'm teaching that class. I have taught both of those classes in the past, and I actually use a different method to explain all of this in that class. So the key is the caller has to set up the stack first to basically say, hey, subroutine, okay, I'm going to store the return address for the subroutine so that whatever subroutine I'm calling knows where to go back to when the subroutine is done. And then from the perspective of the subroutine being called, it makes the assumption that the caller, wherever the caller is, okay, it doesn't matter who the caller is or where the caller is, whoever is calling me has already stored the return address on the stack. All I need to do at the end of executing the subroutine is to retrieve or pop that return address and use it to continue execution. So are we kind of doing this okay or not? I think it's mostly okay. All right, so now we can look into how this code translates into assembly code using the TTP ASM. So I'm going to use exactly the same program. And I cannot remember how to split a screen vertically. So I'm going to use a -o on the outside. I think it's lowercase o, but I could be wrong here. Nope, that's the wrong one. is uppercase O for vertical split. There we go. Now you can start to see why I like, Vim. I mean, you can obviously do this with a lot of different editors, but this one doesn't need to have the GUI installed. Okay, I could be running the Linux in console mode, and I'll still be able to do this. All right, so the first thing is we need to implement this program. Let's start with a no op, okay? Because every time if you want to use the trace analyzer by running Logisim in CLI mode, you need to start with a no op. So it's just a good idea to start with no op, okay? And I'm going to follow the order of this thing and just say, this is the subroutine F. So defining a subroutine in assembly code really is just that simple. Okay, you just have to have a label that is the name of the subroutine defined, and then you put the content of the subroutine, over here. Well, this subroutine doesn't do a single thing, so we'll just say, use a no op to represent what the subroutine does. Now, this no op is not really needed, okay? But I'm just using here the no op to represent the body of the subroutine. But now it is time to return to the caller, and we have to first retrieve, pop the return address from the stack, right? So we'll just write down, we'll pop return address, and then we'll say continue execution based on the return address, because we don't really know, what is the stack pointer? We don't have a stack pointer, do we? Okay, so now we move on to main. Yes, we know we have something unfinished in F, but we'll move on to main regardless. Okay, the first thing we want to do in main is to push the return address on the stack, and the next thing we need to do, this one we do know, continue execution at F, JMP I to F. Okay, and when it returns, we want to do the same thing, push return address again. This is for the second call of F, and then we have another JMP I after this. Okay, and main has a return 0 in C, but since in assembly code in the toy processor there's no operating system to return to, so we just replace the return 0 with a halt instruction to basically signify that, well, we're all done here. All right, so we got a few things to resolve. The first one is if we just do a no op here and then the definition of F, the program is going to continue execution right where the definition of F is, which is not the right thing to do. So we're going to do a JMPI to main right away because of the ordering of how we define the subroutines. Now, if I define main first, then I wouldn't need JMPI to main. But since I follow the same definition order as in C, I define the subroutine first. So that's why I have to jump around the definition of the subroutine so that we actually start to run main first and not running the subroutine F first. Okay, so now we got a few questions. Okay, and there's one more here. Okay, so now we also have to look into how to initialize the stack pointer. Okay, so we got quite a few questions. The convention of the stack, at least in the case of the toy processor, is the rest of RAM. Okay, if the portion of RAM that is not being used to store the program, they're all stack. Okay, so that means the stack is starting after the very last instruction of the program, which is the halt instruction, and all the way to location FF in RAM. Okay, so now the question is, well, how do we initialize the stack pointer? We initialize the stack pointer to not location FF, but the one location that is past it. So it's 100 in hexadecimal. And then somebody's going to say, but Tech, 100 in hexadecimal cannot be represented using only 8 bits. And you'll be absolutely right about that. So we only store the least significant 8 bits into the stack pointer. Okay? The next question is, but Tech, there's nothing in the processor. Let me just kind of pop this into the view, your view, for a little bit. There's nothing here in the entire processor architecture that is labeled SP or stack pointer or anything related to the stack. And you'll be right about that too. Okay, we do not have a dedicated stack pointer. So what we're going to do is we're going to have a convention, and we say, well, let's just agree to use a particular register as a stack pointer. I have just lost my mouse pointer, but it's back. All right, so the first thing we need to do is to mention this part here, right there. So we use register D as the stack pointer. Now this is just a convention, which means it is not hard-coded into the processor architecture itself. If you look into the architecture, register D is just like the other three registers in every way imaginable. Okay, so it is by how we use the register by convention that we say, from here on in this class, we're going to use register D as our stack pointer. So to initialize the stack pointer is now an LDI D0. Because remember, 0 is really the same thing as hexadecimal 100, because we cannot store that extra 1, which is bit 8. We can only store bit 0 to bit 7. And it's going to work out, because the first time we decrement D, it's going to go from 00 down to, guess what, FF in hexadecimal, which does point to the very last location in RAM. So that's how we initialize the stack pointer. But now that we know where the which register is being used as a stack pointer, pushing is now not too difficult. So because in pushing, the first thing we want to do is to decrement the stack pointer. Decrementing register D is pretty easy because we just say decrement D. Okay. The next thing we need to do is to store the return address on the stack, or where the stack pointer is pointing to. This one is a little bit harder. Okay, so this is what we want to do. Okay, and we got two challenges. The first one is how do we know where we are supposed to return to? So at this point in time, I'm just going to use a label to store that. Okay, so L1 is where we need to get back to when the subroutine is done. Because if I jump back to the JMPI instruction, I'm just going to call F again, but it is still the first call to F, which is not what I want to do. I want to move on to the second call to F. So L1 is the label that that's the continuation point. When the first call of F is done, then it needs to continue at the label L1. Okay? So L1 is our return address. But I cannot do something like this. Now, I wish we could sometimes. I wish we could just do something like this. Okay? Because that's what we want to do. Because we just want to store the label L1 to where the stack pointer is pointing to at this point, because that would implement exactly what the C code needs to do. But it doesn't work, because the only thing that we can store indirectly into where another register is pointing to is a register. So what we need to do now, and you can see, that line is, okay, let me turn on line numbers here. So you can see how line 18 is highlighted in red. That means it doesn't work. Okay, that's one good thing about syntax highlighting, is it really highlights what can and cannot be do from the syntax perspective. So what we need to do is to use another register, let's say register A, and say, well, we'll put L1 into register A first, and then we'll store register A to the stack. That will get the job done. Okay, so you can probably imagine that when we need to call F the second time, it's going to be the same kind of setup. Okay, first thing, decrement the stack pointer, and the second thing is to store the return address. But this time I cannot use L1 anymore, because L1 is the point to return to only for the first call of F. For the second call of F, it has a different point to return to, which I'll just call label L2 for the time being. Okay, that's the address of the halt instruction, because that's once we return from the second call to F, we're done. Okay, there's nothing else to do. Okay, so we're going to use the same approach, LDIA with L2, and then we STDA, oops, like so, and then JMPF. this is from the perspective of the caller. The next question is, well, okay, now that we know how to store the return address and then continue execution at a subroutine, what is the subroutine going to do? The first thing we want to look into the subroutine is to say, we can cheat a little bit here because we know register A still has the return address by the time we get into the subroutine. Maybe we can just use that. So what I'm going to do is to basically say, guess what? A subroutine cannot make assumptions about what is in a register except for register D. Okay, so except for the stack pointer, a subroutine cannot make any assumptions about registers A, B, or C. Okay, and to emphasize that, okay, I'm gonna say LDIA with some junk value here. Okay, 172, LDIB with 45, LDIC with 79. Okay, now does the actual C code specify that? No. But can I do this over here? The answer is yes, okay, because the caller cannot expect registers to remain the same, after a subroutine is called, and a subroutine should not assume registers to have specific values, from the caller, except for register D being the stack pointer. So if I were to, add all of these lines from line 5 to line 8, are we introducing additional time in the execution of the subroutine F? The answer is yes. But is this particular implementation of F, is it still quote-unquote correct? Is it still consistent with what the C code is specifying? The answer, interestingly, is also yes, because the C code doesn't say that I cannot change registers in a particular way. Okay, there are no instructions, there are no statements in F to do anything whatsoever. So if I just want to put some random values into registers A, B, or C, hey, it's not inconsistent with what the C code is specifying. I'm just burning cycles that is doing nothing productive from the C code's perspective. Okay, so now when we say, how do we retrieve the return address? We kind of know that, right? But we have to retrieve the return address to a register. So that is a LD instruction. So LD, and you can pick any one of the 3 registers, A, B, or C in this case. Let's just pick register B, okay? So this is going to do the same thing as B is getting whatever the stack pointer is pointing to, because remember, register D is being used as the stack pointer. But we have one more thing that we need to do, which is increment D, because if you look up the C code, the next thing we need to do is to add 1 or increment the stack pointer. So this is where the one instruction that we haven't talked about yet needs to be here, okay? Because we now know that where we need to go back to is in register B. The content, the value of register B is the address of where we need to continue execution. So basically what we need to do is really this, okay? Hey, program counter, copy B's value into yourself so that the next fetch operation is going to the continuation point in main, okay? This is what we want to do. If you are to look up the opcode table, which is also very useful and important in exam 2 tomorrow, okay? If you were to look up the opcode table and you ask, do we have any mnemonic to do this, okay? Can we change the program counter to one of the 4 registers in the register bank? There's one. That particular instruction is JMP without the I, okay? So this is very important. It is without the I, and instead of an immediate, it is a register. So JMP-B in this case is doing exactly what line 13 is commenting. It is copying the value of register B in the register bank to the program counter. So this way, after the JMP-B instruction, the next fetch cycle, the next fetch of the instruction execution cycle is going to wherever B is pointing to get the next opcode, which in this case is going to be L1. All right, so I'm looking at the watch here because I need to go to a meeting. But before I do that, I can be slightly late to that meeting. I think I'll be forgiven in that case. So what I'll do is I'm going to actually run this code in the CLI mode of Logisim. And then you guys can go ahead and look at the trace of that one. But I do want to demonstrate that it does work. Okay, so we'll do this. So we're going to cat this to xclip, cell clip. So now it is in the clipboard. And then we'll switch back to here. And the assembler is already in place. Some of you were asking, which assembler should you be using? And this is the assembler that is just known as assembler. Okay, this is the assembler known as just assembler without being obsoleted. All right, so we paste the code in here. Wait for it to assemble, making sure there's no error. Okay, and there are no errors here. And then we go to the RAM file tab, which is right here. We download the code. And I typically just save it with the name of the program, which is stack. So this is stack.csv. But we are not going to run Logisim in GUI mode. So let me close that first. There we go. And we switch back to the CLI, the command line interface, and we'll run everything using the CLI. So we say java-jar where the Logisim file is located. So that's going to be in my documents folder, CISP310, Logisim310.jar. Then we supply the path to the processor file. Okay. So the way you do this in Windows is going to be different because Windows has a different way of dealing with CLI. I'm just moving this up so that the clock is not interfering with this. This is in CISP310 processor, and then processor 0003.circ, and then we have a dash tty table to switch to CLI mode, dash load to specify the content to put into RAM, which is in the same folder, which is the temp folder, but you can always specify the full path, and it's called stack.csv. The output is redirected to stack.tsv. Okay, so you have to be careful with the extension of these two. One specifies the content to put into RAM, and the other one is the actual trace. The easiest way to remember this is T for trace. Okay, instead of T for tab, T for trace. Okay, so at this point, okay, we are pretty close to the end here, but I kind of still want to finish this discussion here. So now we go to the trace analyzer and go to sheet 1. Okay, so you got to remember all these steps. You might want to put it on a little post-it and then put it, either use an electronic post-it on your monitor or have an actual post-it so that you can kind of remember how to do all of these things. You only need it for a few days because after that you'll basically remember what to do. It becomes a kind of a form of muscle memory. All right, so there's that, and that, and that. Now we do the import, and then we switch to analysis. Okay, so the key point, in this one, is you kind of have to switch between this and the assemble view inside the assembler. Okay, and to be more specific, you can, if you want to hide some columns that we don't really need to use, go ahead and do it. We don't really need to look at everything, but it is really kind of helpful if you know where L1 and L2 are located. Okay, so L1 is defined on this row, and it is basically 15 in hexadecimal. or 21 in decimal, and then L2 is further down. So L2 is defined over here, which is basically 1B in hexadecimal or 27 in decimal. Okay, so when you look at the trace, there are a few things. Okay, you can go through this line by line. You can go through the trace analyzer, line by line. That's something that I would like you to do. Okay, because I think it's going to be beneficial. But the more specific item that I want you to do is to figure out, how the stack is being used. Every time when you see in column C that an item or one location of RAM is being updated or overwritten, that is, in this program, that's an update of an item on the stack. That's a push operation. So you can now see how we push 15, which is the return address L1, on the stack. And then we continue execution in the subroutine. Now, how do we know that we just continue execution in the subroutine? It's because the program counter changed from 13, which is in main, to 03, which is the first byte of the subroutine. Now, how do we know that? We switch back into the assembler and then go back to the assemble view. And this time we are looking up the label F. And label F is on line 4, and you can see how F is defined to be the address of 03, the no-op instruction. So now the question is, what about the return operation? What do we do? Can we look in the trace and find out what we do when we're actually returning? That's on line 10. Okay, so on line 10, we know the address is 0A in hexadecimal. So we go back to the trace, and then we look up, column A, which is basically the program counter, and we look at 0A, which is right here. So at location 0A, what we did was we read certain items on the stack. Okay, to be more specific, we read location FF, and guess what? FF is exactly where the stack pointer is pointing to, because register D at this point is still FF. And then we retrieve the content at location FF into register B, and that's why register B got updated to 15 in hexadecimal. 0B, at location 0B, we only increment the stack pointer. So the stack pointer, which was FF, is now incremented to 00. Okay, and 0C location is the JMP-B instruction, which is basically just changing the program counter to whatever register B has. So that is why the next location to execute is not whatever is right after location 0C, which is location 0D, but instead it goes back to location 15, which is where L1 is defined. So this is how we continue execution in main after the first call of the subroutine. So the second call of the subroutine is really kind of the same deal, except for one thing. What we push on the stack is now 1B, because 1B is label L2, and this is how the second invocation of F knows that we are not going to return to L1, we are supposed to return to L2, because it is all because the caller, main in this case, is pushing the correct return address on the stack, and the subroutine is just blindly assuming that the stack pointer points to the correct return address. In RAM read, what is 17 and 18? Okay, so that's a good question. 17 is the immediate of line 16, and then 18 is registered here because when we changed the program counter, when the program counter is incremented because of the LDI instruction, that's a change of one of the output pins of the processor, so it got logged in the process. Does that kind of explain what's going on? Because an LDI instruction, at location 16 is our LDI instruction, and the LDI instruction needs to read the byte that is after the opcode. That's the first read over here. But after that, it also increments the program counter. Incrementing the program counter is causing Logisim to create another log entry. So that's why we have this second log entry, because one of the things that the LDI instruction does is to increment the program counter. Yeah, so what Catherine is mentioning has to do with what is being logged, what is triggering an entry in the log in Logisim. It's basically any time one of the output pins got changed. And all the registers, the program counter, the microcode pointer, not the microcode pointer, but the program counter, the actual registers, even the address bus, they all got an output corresponding output pin. So if any one of those items is changed, during the execution of an instruction, it creates an additional line in the trace, and that's why we see these kind of extra items over here. Because that's actually reflecting what is going on inside the processor, even though for LDI instructions, for the most part, we don't need to pay attention to column B, but instead we should pay attention to column D because they're supposed to update a register. So we do contain some extra items that doesn't need to be seen in the analysis tab. They're just really extra stuff. All right, so the time is 10:11. I really need to go because I'm already 11 minutes past where I'm supposed to be in a meeting. But I do have a second half of this lecture that's already pinned and is labeled in Discord as end of lecture of today. So yes, I did a little bit of time traveling to get that part done. So let me just give you guys the key to the lab. The key to the lab is, so there is a new lab, which, I haven't released it yet. So, okay, I'll quickly do that part so that you can access the lab. It is due next Monday, so don't sweat it, in terms of, but I need time to study. It's not due until next Monday. So let me change that first. Exam time, yeah, I will be working out the exam time after the class, after my meeting today. So I will send that out maybe around 1 to 2 today. Yeah, I'm sorry that I'm running a little bit behind because there was a family emergency that is still going on. But I'm good. I just need some extra time to get this done. Yes, so I was about to release the lab. So the lab is stack operations. I got the whole thing set up already. I just need to set the time when it's due. So it's going to be next Monday. Next Monday is, let's see, today is the 15th, minus 2, 13th, the 20th. Thank you. Excuse me. July 20th, 9 a.m. There we go. All right, so we got the lab released. If you have time to work on it today, great. If not, you can probably work on this after the exam tomorrow and over the long weekend. Cool. So I'm gonna sign off right now. When I'm done with the other meeting, I'll come back to Discord and answer the questions that you guys have posted. But right now, I just need to go to the other meeting. All right. Well, if I don't get to see you guys again, good luck with the exam, which is not something that you should rely on, but nonetheless, this is what I'm supposed to say. All right, so I'm gonna disconnect at this point and post questions on Discord. I'll get back to you guys after 11 o'clock. Okay. All right, where's my